Listeners, TAs. My name is Nico Dreyer, and this is my physics project number 2. Similar to the first project, I did this project alone. I didn't think I would be assigned a new group because the first project, my group was unresponsive to my emails, and it turns out one of them had actually dropped the class, and the other one just wasn't responding or showing up to the studio. For this project, I assumed that would be the same, so I went ahead and did the project by myself. Alright, let's get started. So this slide displays the problem that I chose to do, which was the third problem involving the disk. Each disk essentially acts as a Newton's third law pair force against the opposing disk, meaning that the force given above is positive for one disk and negative for another. Each disk initially has a distance of 2r from each other, where the radius of each, which is the radius of each disk added together, assuming capital R is equal to the radius. I, are then asked to find the maximum speed of each disk, which is the absolute value of the velocity function for a given disk with its respect to mass, which I later go on to solve. This slide contains the necessary assumptions that were useful for this project. So if forces are not directly horizontal from one another, there's going to be some type of angle to this project and the force being exerted from each disk to its other disk, disk A on B or disk B on A, that throws off any measurements by a certain angle factor. Also, there is the assumption that this table is not truly 100% frictionless with no resistance whatsoever to affect the system, which is a pretty good assumption, so there's no friction being done by work. I should also note that in order for this problem to have a valid solution that I later describe, the initial distance must exactly be that of 2r. Finally, I am assuming that after the disks are released, there is no outside or air resistance against the movement or buildup of kinetic energy that occurs as a result of this movement. So this is my initial diagram as force versus distance in meters on the x-axis. My origin for this problem I chose to select as 2r, which I decided is the initial position for my data. The force function, as expected with the 2r divided by x to the power of 6, is an exponential function ultimately, with x increasing, and as x increases the force would go down, which as expected. I also showed an initial bar chart with energy for the system off to the right, which depicts no energy in the system initially. I made the assumption that there is no initial energy and that the force going into the system as work, such that the initial energy of the system is 0, and work will enter the system as the position increases. This means that due to the respective velocities of the disks increasing with a certain distance, the overall change in energy of the system will be positive due to external work done on the system by the force each disk will exert upon one another. I also chose to set the initial force, or F0, equal to 10 newtons, just to make everything readable and just have a nice little value for it. So this slide contains my general understanding of the project. Some things to note is that work is equal to the integral from the initial position to the final position of the force equation, which we are given by F0 is equal to, F of x, the force, is equal to F0 times 2r divided by the position to the power of 6. Kinetic energy is equal to 1/2 mv squared, obviously. The final velocity is going to be what we're trying to find. Initial velocity of this system is 0 because the objects are being held together. And also, it is nice to note that the integral of force, or work, can be set equal to the kinetic energy of the system, or the change in kinetic energy, which is pretty useful, which is what I will use to find the velocity of each disk. So this is part 1 of my calculations. Skipping over the actual messy math, I integrated the force function we were given from my initial position, which is not 0, my initial position is 2r, or the radius of each disk, to some unknown position that I decided to label as x. And as you can hopefully see, I integrated this, and it came out on the bottom right corner with some nasty number, which I then set equal to the kinetic energy of the system in part 2 of my calculations, and solved for final velocity. Now notice my final velocity for each disk will be respective to its direction. So I'm just going to call the direction that disk B travels in positive. So my final velocity is going to be positive. And the direction that the velocity of A travels in is going to be negative. But if we're just talking about speed, then it's just the absolute value of velocity, which is, they're both just going to be positive in the end. and each disk velocity is with respect to its mass, but that is the only difference between the final speeds calculated, because each disk exerts the same amount of force upon each other and only has a difference in the factors of the mass of A or the mass of B, as seen by my calculations. So the final speed is equal to the square root of 4 times the force, initial force, times the radius, divided by 5 times the mass of the respective box. All of that multiplied by negative 32 times r, capital R to the fifth, divided by the position to the fifth, plus 1. And that plus 1 will turn out to be important later on. This is my final diagram. As you can see, it is a square root function starting somewhere near 0. I set my mass just equal to 2, and I set my radius also equal to 2, just so I can get some nice numbers and actually have a functioning system that works. And I have on the y-axis velocity or speed versus position on the x-axis, and I have a little energy bar chart off to the right that shows the increase of kinetic energy done by work on the system, because work entered the system and put kinetic energy into the system, ultimately resulting in my velocity. So here's part 1 of my sense making for this problem. For part 1, I decided to check the units of my velocity function as shown by pretty much everything on this slide. When I cancel everything out, put all the units in for respective values, I get meters per second, which are the units of velocity or speed, which is, well, that's pretty much what I would expect for this. So part 2 of my sense making is reasonability. The quantity discussed in this problem is that of velocity, or more accurately to answer the problem, speed. The function generated as a result of my calculations appears to be correct, because as x increases, the velocity will slowly decrease and eventually bottom out at a certain value, as well due to x being at the bottom of the equation I solved for. The speed for either disk will decrease gradually as the position increases, which is very reasonable, assuming that the disk will not continue with an infinite speed and just speed up forever, which is pretty reasonable. It is also worthwhile to note that the velocity speed relative to each disk depends on the mass of each disk, respectively masses A and B. As the mass increases, or if the mass is a greater quantity, the velocity and top speed as the position increases will also be less big than if the disks have a smaller mass. And finally, this is my final sense-making strategy for this problem. So I chose to ultimately set the initial force equal to 10 newtons. I'm also going to choose to set the masses equal to each other so I could just solve one velocity function. So I just set the mass equal to 2 kilograms. The initial radius, capital R, is 2 meters, and the change in position of each disk is 10 meters. When I plugged all of these numbers into my function for, I should just say speed. It's really the final velocity, but speed. It's about 2.814 meters per second, which it's honestly a pretty reasonable number, assuming that if you have a disk that weighs about 2 kilograms traveling 10 meters, it sounds like a reasonable number. 2.8 meters per second, almost 3 meters per second. It's a reasonable number, so that's how I know that my answer makes sense, in my eyes at least. It makes sense to me. Finally, my reflection. This problem is not entirely dissimilar to a quiz problem on quiz 6 that we recently took. The quiz problem told us essentially that an object was moving and then had a force exerted on it and asked us to determine the net work on the system. The problem also gave us an initial function for force as shown above, which this problem also gave us. However, a notable difference between these two problems is that the force in the system put negative work into the system, ultimately slowing the box down, whereas in this problem involving the disks pushing against each other, the repulsive force actually put positive work into the system and increased the system's overall kinetic energy to each disk. Each disk, with respect to its direction outwards, had an increase of work positively into the system due to this force. So in the sense that work accounted for a gain of kinetic energy of each disk system, or a loss, the problem is different from the quiz problem, but similar in the aspect that each system has work put into it externally and that affects the movement of, in the quiz problem, the box, or in the the problem that I was solving above, the speed of the disks. And with that, ladies and gentlemen, or lady or gentleman, I conclude my presentation. Again, I hope you take into account that this was just done by one person, me, myself, and I. And I hope everything made sense, and I hope you enjoyed listening. Have a good rest of your day.